Welcome to the core concepts of solar photovoltaic system. A solar PV system basically consists of number of components, and here you can see that it consists of solar PV modules. Then you can have some breakers or disconnects over here in the cables, and the cables are connected to the inverter. To the inverter we can have a battery bank or the batteries which are connected to the inverter. Then inverter output is connected to another main breaker disconnect. This breaker is connected to one of the breakers in your distribution panel, and the distribution panel on one side is connected to the grid and the other side it is connected to the load. So this is basically a single line diagram of a solar PV system, a basic configuration or basic connections concepts of solar PV system. Let's first see how the solar panel works or it produces energy. Here is a simple diagram of a solar panel or solar module which has been installed on a particular angle at a particular place, and you can see the sun is moving from east to west producing light, and this light reaches the solar PV module. Okay, now the more sun produces light, this solar panel shall produce more power. Now you can see that if the sun is tilted, now let's assume that the sun is at this position as shown, and it has risen from east in the morning, and the current time is, let's say, 10 a.m. Okay, now obviously it will not be at top of its position because it's not 12 p.m. This sun shall be making an horizontal and vertical angle with respect to its position. Okay, now let's assume that this sun is, if we make a horizontal projection over here, and if we measure its angle from with respect to the east, it will be having an angle, and similarly it will have a tilt angle. Okay, so this angle basically its angle with respect to the horizontal surface, and this angle its horizontal projection angle with respect to the east. Okay, now at this point the sun is not able to send its maximum light over the solar panel because solar panel is facing at this angle. As the sun rises, it will change its tilt angle, this one, and its horizontal angle shall also be changing. At noon, the sun will be at this position. Okay, its horizontal angle will be 90° with respect to east, and its tilt angle has also increased because the sun is rising, so its tilt angle with respect to the horizontal surface on earth is also increasing. Now at this point the sun is throwing its light over it, and it is possible that the solar panel is receiving more light from the sun, so it shall produce more power. Now during the winter season, assuming this position of the sun is in the winter position, the sun has particular tilt angle and it's not on top of the solar panel. Suppose we have moved or it's the time of summer, then the sun position has changed and it's relatively more on top of the solar panel. Okay, in this case the sun is able, or the solar panel is able to receive more sunlight as compared to the winter season. Okay, in this case the sun panel shall produce more power. Hence the angles of the solar panel and the sun in combination with each other are very important that how much the solar panel shall produce the power. Now suppose the solar panel is installed flat horizontally on the earth's surface and the sun is exactly at top of the solar panel. It's 12 noon and it is making right angle or is perpendicular to the solar panel module. Then this is the point where the solar panel shall be making maximum power according to its capacity, the capacity set out by the manufacturer. This means the angle of the PV module and angle of the sun together with each other or with respect to each other are very important that how much the solar panel shall produce energy. So in the case where the sun is perpendicular to the or the sunlight is falling on the PV module perpendicular to it, it shall be producing maximum power according to its capacity. Okay. Now there's another factor which also determines how much energy shall be produced, because solar panel has a phenomena. When solar panel works, it works like a machine. So when it works, it heats up. Okay. So during the summer, it generates more heat. When it generates more heat, its efficiency decreases. When its efficiency decreases, the power production capacity also decreases. So the third factor which affects the production is the temperature of the solar panel module. Okay, so the temperature factor basically depends upon two main factors, that is the internal characteristics of the PV module, and second, how much ambient temperature or how much is the environment temperature is there. The more it is ambient temperature, the temperature of the PV module shall increase, and if the temperature of the PV module increases, its efficiency decreases to produce power. Therefore, the more suitable environment for the solar panel to produce energy or to produce power is where there is maximum light is being received by the solar panel under low ambient temperatures, or where there is winter conditions or ambient temperature is, let's say, close to the 0 degree centigrade. Generally speaking, the difference between the power produced during the winter and summer season could be up to 10 to 15%, and this is a huge difference. So it's always preferable to have solar PV modules installed in a way that its temperature doesn't increase so much and there is a cool wind blowing underneath the solar PV modules that shall reduce its temperature. Okay, now there's another factor which we need to discuss is the area of the solar panel module. The more area it has, the more power it shall produce, obviously, because as said before, the solar panel is consisting of smaller solar cells. Cells are integrated with each other to produce power. So each cell, when is receiving the solar light, shall produce the power, and that power shall add it up to produce an accumulated power. Hence, the more area a solar panel has, it will produce more power. So there is a direct relationship between the area and the power produced. Now, as the sun changes its position throughout the year from winter to summer and summer to winter, okay, it will have a particular range of its angle with respect to the solar panel. Now, we need to find out an optimum tilt angle for the PV module so that it can receive maximum power throughout the year. Generally speaking, we need to find a midway between summer and winter season, and that angle can be found out from the sun position during the spring season. Okay, during the spring season, when the sun is more perpendicular towards the sunlight is more perpendicular towards the solar PV module, that angle is more suitable to be selected. Therefore, in general, if the solar PV module is installed with a tilt angle which is more suitable during the spring season, it shall produce less power during the winter and summer season. However, it shall be producing optimum power throughout the year. There could be other way, that is, if we have some moving mechanism underneath the solar PV module so that it can produce maximum power throughout the season, so that the solar PV module moves its face towards the sun when the sun is changing its position to receive maximum sunlight to produce more power. In that case, it shall be a mechanism called tracking system. The tracking system is installed with the solar PV module. Obviously, it is a bit more investment and more expensive. However, for residential and in general commercial purposes, that tracking system may not be installed because the difference between changing the tilt angle of the PV module is not so much. Hence, an optimum angle is selected and the PV module is installed fixed at its location. And what shall be the optimum tilt angle for the PV module? It has been found out through various calculations that the PV tilt angle, PV module tilt angle has direct relationship with the latitude angle of your location. Let's suppose you are located at a location whose latitude angle is 30 degrees. Okay, then the tilt angle of the PV module shall also be 30 degrees, which shall be optimum for whole of the year. That means if you are installing a PV module, let's say this is your PV module, then its angle with respect to the horizontal surface, okay, shall also be 30 degree. So which is the PV tilt angle selected with respect to the your location whose latitude angle is 30 degrees. Now before we look into few more concepts of solar PV system, we need to understand what is energy unit. This is the same unit which you see in your utility bills, okay. Let's suppose we have a bulb, okay. It's connected to your outlet socket and it is 220 or 120 AC, okay, and the bulb is 100 watt, okay. Now if this bulb is switched on for 1 hour, okay, let's say it is for 1 hour working, okay, then what you will do is multiply 100 with 1 hour, and that is 100 watt hours. So the energy consumed or the energy unit consumed is 100 watt hours. If the same bulb is switched on for 10 hours, okay, then this shall be multiplied with 10. 100 watts is multiplied with 10 hours, and that comes 100 watt hours, or in kilowatt, this shall be 1 kilowatt hours. Now this is one energy unit which you see in your utility bill, one energy unit. Hence, a 100 watt bulb running for 10 hours shall be consuming 1 kilowatt hours, which is one energy unit. Let's take another example. If we have another appliance, that is, suppose it's somehow another load which is air conditioner, okay, and that is 1500 watts, okay. Now if this air conditioner runs for 2 hours, let's say 1500 watts into 2 hours, then this becomes 3000 watt hours, which is 3 kilowatt hours. So this 3 kilowatt hours is basically 3 energy units. So 1 kilowatt hour is 1 energy unit. Now we need to understand few basic concepts of sunlight. Okay, suppose the sunlight is being received on the Earth's surface, and this is the Earth's surface. All right. Okay. Now, when the sun sends the light, whole of the light or the whole of the energy is not received at the Earth's surface. The reason is there is atmosphere, and atmosphere has number of particles consisting of various gases and other dust particles. Therefore, when the sunlight starts arriving towards the Earth, it gets scattered at various points. Okay, that means a component of the sunlight reaches the Earth's surface. So the component of the sunlight which reaches directly towards the Earth and which has not got scattered is called the direct component. And the component which got scattered due to the different particles or various reasons, and if it reaches still towards the Earth, this is called diffused component, okay. And some of the component as shown here obviously gets reflected back into the atmosphere, so whole of the sunlight or energy is not received at the Earth's surface. Now the question is, how much energy is received at the Earth's surface? Scientists have worked on this, and they have found out through various calculations that on average the sun energy received is 1000 watt per meter square per hour. What this mean? This means that on average for each hour the sun energy being received at a particular point on earth is roughly 1000 watt for 1 meter square. Okay, if there is an area 1 by 1 meter, this is 1 meter, this is 1 meter, then the sun energy being received in this complete area shall be 1000 watt per hour, or in other words, one energy unit is received by 1 meter square area, okay, at a particular location, and this is a average value. Now this average value obviously changes throughout the year because the sun is changing its position, and there are sometimes clouds, and there are sometimes more particles within the atmosphere, so it's not always 1000, it's not always one energy unit for 1 hour. Okay, so it will be changing. It is also possible that it increases to, let's say, 1200. Okay, and the scientists have found out that the maximum energy it can reach is 1265. Obviously the sun energy doesn't remain constant at a particular location. It keeps changing throughout the day and throughout the year. It's also possible that it comes down from 1000 to 400 at a particular time of the day. Suppose it is 4 p.m. okay, in the evening. So it's possible that it is 400 watt per meter square per hour. Therefore, the sun energy, this is one day, okay, sunrise and sunset. So this graph is showing the power or the energy being received at a particular location. Assuming the 1000 watt per meter square is the maximum energy, so for the whole day it shall be changing. So when the sun is rising for a particular location, okay, the energy being received at a particular location due to the tilt angles or the altitude angles of the sun, the energy being received at a particular location starts increasing, and at noon the solar panel shall be receiving maximum power, and it's quite possible it is 1000 watt per meter square, or even it is less than this or more than this. So for the whole day the sun energy keeps changing. Therefore we need to find out. Therefore we take a standard number called peak sun hours. Peak sun hours refers to those hours, okay, where the energy remains 1000 watt per meter square. Okay, suppose, let's assume this is not the graph. Okay, we assume that the sun energy remains constant like this, 1000 watt per meter square for whole day, and it's like this, this and this. Okay, though it's not happens in reality, but for a moment assuming that the sun immediately rises to this position, okay, and it gets to 1000 watt per meter square at 8 a.m. in the morning, it remains steady for the whole day, and suddenly at 4 p.m. its value drops to 0. Then how much time it has? If it is 8 a.m. in the morning and 4 p.m. it is in the evening, that means we have 8 hours. Okay, so the sun energy remained 1000 watt per meter square for 8 hours. So we will say that the peak sun hours are 8, where the sun energy remained 1000 watt per meter square. But in reality it doesn't happen like this. We can see that the sun energy is changing. So we take an average value or an accumulated value of the sun energy throughout the day, and we calculate through various methods that how much peak sun hours are available at a particular location. It has been found in journal that the average peak sun hours for a particular location are approximately 6. At some location it could be 7 hours, at some location it could be even 5 peak sun hours. So having 6 peak sun hours means that the sun energy received is equivalent to 1000 watt per meter square for 6 hours. So the total energy, okay, if we through some mathematical calculations find the area under this graph, this will be peak sun hours. Okay, this will be total energy being received. Now suppose if sun rises at 6 a.m. okay, at this point it is 6 a.m. and sun sets at also 6 p.m. Okay, that means the duration of the sun is 12 hours. Okay, now assuming when sun rises, obviously it is giving very less light or less energy, and by the time it reaches 7, okay, assume it is giving 100 watts per meter square. Similarly, for the next few hours, it will start increasing. Maybe next hour is 200 watt per meter square, and by noon, it may be 1000 watt per meter square. Then afternoon or in the afternoon, it will start decreasing, and similarly, by the time it is 5 p.m., it may be again 100 watts per meter square. Now, if we sum up this energy content for every hour, let's suppose it comes out 6000 watts. Okay, we summed up this one, this one, this one for every hour. This comes out to be 6000 watts per meter square. Now, if we divide this 6000 by 1000, okay, this will be 6. So this will be called peak sun hours. Again, this means that on average, the sun energy received was 1000 watt meter square for 6 hours. Now the question is, how much power a solar module or solar panel produces? Suppose you go to the market and the seller tells you that he has a solar module of 200 watts, okay? And its area is 1 by 1 meter, assume. This is 1 meter and this is 1 meter. So total area of the module is 1 by 1 meter. So that shall be 1 meter by 1 meter, 1 meter square. Okay. Now this 200 watt solar panel means that it shall produce 200 watts as long as there is solar energy being received 1000 watt per meter square. Okay, this is the condition. Okay, if the solar energy changes, if it is 800, obviously this panel or module shall not produce 200 watts. Now if the solar energy is received for 1 hour, suppose it is 11 a.m. and this is 12 p.m. for just 1 hour, okay, it remains 1000 watt per meter square. The solar energy is 1000 watt per meter square. This panel shall be producing 200 watts at its terminals. Okay, that means 200 watts into 1 hour is 200 watt hours. Okay, and that is 0.2 kilowatt hour, means 0.2 energy units have been produced by this panel in 1 hour. Now there is another condition with this 1000 watt per meter square. Okay, it's not only the one that it should be 1000 watt per meter square, the sun energy, but the other condition which the international standards, which is STC, named as STC, standard test condition, it says that the cell temperature, okay, must be 25 degrees centigrade. Okay, now this doesn't mean that the ambient temperature or the environment temperature it is installed in is also 25 degrees centigrade. No, generally speaking, if the environment is, let's say, at 5 degrees centigrade, okay, the cell temperature or the module temperature itself, because its PV module works like a machine as already said, so its temperature will be higher than the environment or ambient temperature. Generally the PV module temperature is 15 to 20 degrees centigrade higher than the environment or ambient temperature. Okay, so that means if 5 degrees centigrade is the ambient or the environment temperature, we can add 15 or 20. Okay, so that shall be 25 degrees centigrade. Okay, now as the STC condition says that there are two conditions. One, the sun energy should be 1000 watt per meter square and the module temperature should be 25 degrees centigrade. Then at that time, if the module rated, if the module is specified as 200 watt by the manufacturer, then it shall produce 200 watts or watt hour energy units. Otherwise, if the temperature increases or the temperature of the module increases or the watt or the solar energy is different, the module shall produce different watts. Now this thing can be stated in another way. Okay, we said that 1000 watt per meter square of sun energy is being received. Okay, now if the area of the PV module is 1 meter, okay, by 1 meter, okay, and module efficiency is also stated by the manufacturer. Nowadays it is roughly around 20%. What this means? This means that 1000 watt per meter square of the sun energy being received, if multiplied with 20% of the module efficiency, this will give the rating of the PV module. So 1000 multiplied by 20%, or 1000 into 20 by 100, this is 1000 into zero point 0.2, and that shall be 200. Okay, so this is another way to find out what is the rating of the PV module. So again, 1000 watt of the solar energy or the sun energy, when multiplied with the efficiency of the PV module, gives us the rated power of the panel modules. That means that not whole of the solar or sun energy is transformed into electricity or power. It has got an efficiency factor which is 0.2 or the 20% roughly nowadays the cells being produced in the market. Therefore, only 20% of the sun energy is converted into electrical power. Now here we assume that the area of the PV module was 1 meter square. Okay, now let's double the area. Okay, we assume that the area of the module is 2 meter square. Okay, so what will happen to the rating of the PV module? Obviously, more sun energy is being received now. Okay, so this area will give us 200 watt, and this area will also give us 200 watt. That means doubling the area. Okay, we double the area, the rated power of the module shall also double, so that shall become 200 plus 200, 400 watt module. One important point which you must remember is, that is, when we assume that the sun energy being received is 1000 watt per meter square, then it doesn't mean that the sun can be at any angle. No, the sun energy must be coming perpendicular to the PV module. Okay, if sun is at some other tilt angle, then part of the energy is received. Suppose this is the PV module. Okay, this is the side view. Okay, this is the horizontal surface, and this is the sun. Okay, now here at this point the sun energy or the sunlight is exactly 90 degree or perpendicular to the PV module. So this is the ideal situation. 1000 watt per meter square will all be considered. But assume that the sun energy is not perpendicular to the PV module. Sun suppose is at this point. Okay. Now this angle is not 90 degree. Okay. So only part of the sun energy shall be considered, and it is trigonometric calculations through which we will find out that how much sun energy can be taken or considered for calculation purposes. Basically, the sun angle, which is, or the sun component, which is at 90 degree, this component, okay, shall be basically be considered as the sun energy. The reason is that the total accumulated energy being received by the PV module shall be equivalent to this part, and this is a trigonometric calculation. We can find it out through trigonometric calculations because we know these angles. It's not part of, or it's not scope of this presentation. Anyhow, it's just to let you know that only component of the sun energy can be considered for calculations, and that can be easily find out. Now the question is, if we have more than one PV modules and they are connected in series, then what happens? Now each of the PV module have two terminals, positive and negative. Okay. Now each PV module, you can consider that it acts like any other battery cell. You have used battery cells like a AA or AAA battery cell, right? So assuming each PV module is like a battery cell, and we can connect them in series. Series means that the negative of one PV module shall be connected to the positive of the other, and negative to the positive, negative to the positive, negative to the positive. This way all the PV modules are connected in series, okay? And the last terminal, which is the negative of the last PV module and the positive of the first PV module, can be used to be connected onwards to our system, which is in general the inverter. Okay, that shall be the inverter in. Now let's assume that each PV module is 500 watts. Okay, and each PV module, when it is operating, it produces 40 volts. Okay, it's not a double A 1.5 volt battery. The PV module volts may go up to 40 volts, 45 volts when it is operating. Okay, now when we connect them in series, okay, these volts of the PV modules shall sum up. That means they all shall sum up, okay? And if there are 10 modules, okay, this shall be 400 volts while this combination of PV module is operating. And how much power? It shall be 500 obviously into 10, and that shall be 5000 watts. Now this set of PV modules shall produce 5000 watts for 1 hour if we remember the conditions are fulfilled that the sun energy is 1000 watt per meter square is being received, and the ambient temperature or the cell temperature, precisely speaking, is 25 degrees centigrade, or the temperature of the PV module is 25 degrees centigrade. Hence, two conditions: 1000 watt per meter square of sun energy is being received, and the second is that the PV module temperature is 25 degrees centigrade. In that case, this combination of PV module shall produce 5000 watt for 1 hour, or 5000 watt hours, or it shall be 5 kilowatt, meaning 5 energy units shall be produced. Now, if we have for a particular location where these combination of PV modules are installed, let's suppose the peak sun hours available to us are 6, okay, for this particular location, which means if we repeat our lesson again, that 6 peak sun hours means that 1000 watt per meter square is available exactly for 6 hours and not more than that. This means the rated power of these PV modules, which is 5000, if we multiply it with 6, this shall be 30,000 watt hours, okay, or this is equal to 30 kilowatt hour, which means 30 energy units shall be produced in one day, remembering that 6 peak sun hours is a value estimated for a location for one day. So 30 units shall be produced by this setup. In reality, it doesn't happen like this. We calculated 30 kilowatt hours or 30 energy units shall be produced, but it's not like this. The reason is there are a number of losses in the system, or number of losses shall occur or take place. The first loss is due to the temperature. Remember, this 30 energy units we have calculated is based on the condition that the temperature of the module remains 25 degrees centigrade, which doesn't remain in reality. The reason is as the ambient temperature increases, the temperature of the PV module also increases. With the increase of the PV module temperature, its efficiency to produce power decreases. Therefore, the power reduction takes place, okay, and this process continues for the whole day and throughout the year, okay. So this is one factor, okay. And the second factor, there are a couple of other losses like mismatch loss. Mismatch losses are those losses in which there may be differences between the PV modules at the minute levels, and those minute levels we shall see in the coming slides that they also contribute to the losses, and the ultimate power is not what we have calculated ideally here, okay. Another factor which can contribute to the losses is the voltage drop in the cables, okay. No cable is ideal, and the power is lost while the power is transferred from one place, from the set of PV modules towards the inverter. The loss of the power shall take place, and that may be up to 2 to 3%. So losses due to the cable or voltage drops in the cables. Okay, so this is another reason that not ideal power is transferred. Another factor is that with the passage of time, obviously the PV modules never produce power as they produce from the very first day, because they degrade with the passage of time. So with the passage of time, their performance decreases, and the time comes that they may produce power, let's say 20% less than what they produced from the very first day, when they have passed 20 years. Okay, so that is another factor. So there are a couple of losses which contribute in decreasing the performance of the PV system, and it can be verified through calculations for a particular location, though it will require hundreds of calculations. But on an average, it can be stated that for a particular location, the total losses are roughly from 25 to 30%. Okay, the losses which we have just discussed. This means the system efficiency is 100 minus 25%. If the losses are 25%, then the system efficiency is 75%. So if we have calculated 30 energy units previously, okay, we shall multiply it with 75%. Okay, so that becomes 30 into 0.75, and this is 22.5 kilowatt hours, which means 22.5 energy units shall be produced by this set of PV modules in one day for a particular location on an average. Now this value 22.5 kilowatt hours or energy units being produced by this set of PV modules in one day, it doesn't mean it shall always be 22.5 kilowatt hours or energy units. It may be higher than this, or it may be even lower than this. Suppose there is a dust on the PV modules on a particular day. Okay, the dust has accumulated, so this shall also contribute to the losses of the PV modules. Suppose there are clouds on a particular day. Suppose it's a rainy season, or due to some other reasons there are more particles, and the sun energy being received is not 1000 watt per meter square. Okay, so on an average, it has been found that the maximum power you can take, or the maximum efficiency you can take, is just 75%. So generally it shall be lower than this, in the range of 65 or 70%. So in our case, it shall be around 20 units, energy units, for this particular location where we have considered 6 peak sun hours. Okay, so if the peak sun hours increases, if it increases to 7, definitely we will have more energy units, and in that case our system will become more feasible and more usable for our load. Now what we have discussed and learned, let's summarize this in a formula. Okay, suppose we need to find out what system rating we should select for in our case. Okay, or how many number of modules we need actually. Okay, so this formula is system rating. Okay, system rating means how many kilowatt of system we need. That shall be equal to sun energy sun, into efficiency of one PV module, okay, into total area. Now the total area refers to the area of all the PV modules. Okay, this can be further written as E sun energy, which is 1000 watt per meter square we discussed, and efficiency of one module specified by the manufacturer, into total area. We can write this like area of one PV module, okay, into quantity of PV modules. All right, once again, this is system rating, okay, in kilowatts. E sun is the energy of the sun being received. We discussed 1000 watt per meter square. Efficiency is the efficiency specified by the manufacturer for one PV module. Okay, this is M, into area of one PV module into quantity of PV modules. Let's take an example. Okay, this is the actual data sheet of one of the Canadian Solar's PV modules, and we are selecting this model. Okay, this is the model number 640MS. Its nominal max power, okay, its rated power specified by the manufacturer is 640 watts. Okay, forget about the other parameters, we will discuss it later. Okay, here the size of the PV module is given 2384. Okay, this is 2384 length of the PV module, and 1303 is the width of the PV module in millimeters mm. Okay, now the total area becomes 2384 into 1303. If you multiply this, and this is mm. Okay, we can write this in meters. So in meters shall become 2.384 into 1.303. So this will become approximately 3 meters square. Let's use this data in our formula. Now suppose we want how many PV modules we need if we want to install a system of 25,000 watts, suppose. Okay, so what we are looking for, we want a rated power of the system 25,000, and E sun is the 1000 watt per meter square standard test conditions, or the standard value of the sun energy, into efficiency. Okay, efficiency of the PV module can also be selected from the data sheet. This is here 20.6. Okay, so we will write 20.6% into area. Area we found out for one PV module was 3 meters square, and into quantity. Okay, so that becomes 25,000, 1000 into 20.6 divided by 100, because it is in percent, so we will divide it by 100 into 3 meters square into quantity. Now if we solve this equation, 25,000 into 1000 into 20.6 into 3 divided by 100 into quantity, so we can solve this, and Q becomes approximately 40. Okay, so we need this PV module, we selected 640. Okay, so we need 640 rated PV modules in quantity of 40 to have the PV system rating of 25,000. Okay, so 25,000 watts or 25 kilowatts will be the system rating selected. Now in this equation we have assumed that the sun energy is 1000 watt per meter square and efficiency is 20.6%. Okay, now remember from our previous discussions that it's not always possible, or in reality this 1000 watt per meter square will be changing. The efficiency of the PV module will also be changing, because due to its temperature factor this will change. Due to the different sun energy and due to the change in efficiency, we may need more quantity of the PV modules. So let's calculate that. Now for a location, it has been found that an average value of sun energy 800 can be taken. Okay, this is average sun energy being received at a particular location. It could be 1000 as we discussed, it could go up to 1200 watt per meter square, but for an average calculation we can take 800 watt per meter square. And for efficiency, the 20% or 20.6% specified by the manufacturer is at STC condition. So what is STC condition? STC, if you remember, that the temperature of the PV module should be 25 degrees centigrade. Later we will see that we can find out the efficiency of the PV module at different temperature, and that is also given indirectly in the data sheet. However, we will see it later. But at this moment, let's say the efficiency decreases by, let's say, 3%. Okay, so that means 20.6 shall become 17.6%. For a moment, assume, okay, due to the increase in temperature or during summer season, the efficiency of the PV module decreases and this will become 17.6%, okay. Area of the module remains same, which is 3 meters square, and quantity we need to find out. So once we solve this equation, okay, Q becomes 59 approximately. Okay, so we can see that the number of PV modules we need more once we are assuming that the sun energy shall not be 1000. Obviously, when the sun energy is less than 1800, we need more PV modules to generate or to have the system rating of 25,000. Okay, and the efficiency has also decreased. Therefore, the number of PV modules have increased. Now, if you recall our previous discussions that how many energy units a rated system power shall produce, let's do it again. So, taking this 25,000 watt rated system, we shall convert it into kilowatt by dividing it by 1000. Okay, this will become kilowatt. And let's take the 6 peak sun hours. Okay, taking 6 is good average value for our calculation, and taking system efficiency or taking losses 25%, meaning 75% efficiency of the overall system, and this becomes approximately 112 kilowatt hour energy units. This means 112 energy units shall be produced in one day at particular location, considering all the previous data we have just discussed. Now let's understand few more concepts about the PV module, okay? Before you get into designing or further understanding of the PV systems or PV modules, you must understand what are the behaviors of voltage and current supplied by the PV module, or what is the relationship between the voltage and current supplied by the PV module. Okay, now let's assume we have a PV module, it's placed in the open space and it is receiving sun power. Okay, so there is sun and sunlight is being received by the PV module. Okay, now this PV module has two terminals which are available through a cable underneath, and both of them can be connected to a load. Let's for a moment assume that this PV module is not connected to any load. So this positive terminal and this negative terminal, if connected to a voltmeter, okay, let's connect it. Let's connect the negative lead to the negative terminal of the PV module and the positive lead to the positive terminal of the PV module. Then this PV module shall give you a reading on this voltmeter. Let's assume it's giving a reading of 45 volts. Okay, we will call this 45 volts at voltage open circuit. Open circuit means that there's no circuit and there's no load, and we're just measuring the voltage over the terminals or across the terminals of a PV module, and assuming it is giving right now at 45 volts on a particular time of the day. Okay, now let's connect a load to this PV module. Okay, now this is positive and negative terminals of the PV module. Assume we have a load which is a bulb, and we further assume that the power being supplied to this bulb can be controlled through an associated control or a device which has a knob over it. Okay, and we can rotate this way to control the supply to the bulb. Okay, now assume that we are also measuring the current through this circuit, and we will place an ampere meter over here. Remember, the ampere meter is always placed in series within the cable. So this is the terminals of the ampere meter, excuse me, and we will connect over here like this. Okay, now this negative shall be connected to this control device, and this is connected to the bulb. Okay, at the same time we are also measuring through a voltmeter, okay, the voltage across the terminals of the PV module. Okay, let's connect over here and let's connect over this. Okay, Now we have voltmeter, we have ampere meter, we are measuring the voltage and ampere, okay? And what we will do is we will start rotating this knob towards the right side so that we can start supplying power to the bulb. Once we start rotating, assume it has 10 steps. This knob has 10 steps, okay? And we first rotate it first step out of 10 steps, and while doing this the bulb will start glowing on, and at the same time we are recording the values of voltage and ampere, okay? And we have a table over here. So what we will do is that these are the steps of the knob, okay? 1 2 3 4, this and 10 steps, okay? This is the voltage and this is the current we are measuring, okay? Now at the step 1 it's possible, okay? At step 1, before that, there is step 0. Step 0 means it is off and no power is being supplied. And step 0 we can consider as there is no circuit, okay? And the voltage open circuit, if you remember, was 45 volts in our previous slide, okay? Now at step 1, once we start giving power to the bulb, assume the voltage is, let's say, 43 volts and the current is 5 amperes. Okay, now let's rotate more this knob towards the next step, and that is step 2. Okay, now once we are at step 2, assume the voltage measured is 42 and the current measured is 10 amperes. Similarly, we will keep rotating this knob towards the step 10 and we will measure the ampere and current, okay? Let's assume that at step 3 it is 40 volts and the current is 15 ampere. At step 4 we are at 38 volts and we have 20 amperes, okay? And assuming that at step number 8, okay, we have 35 volts and we have amperes, let's say 14 amperes, okay? Assuming that this PV module can supply maximum 15 amperes, okay? Now at step 10 we can assume that the voltage measured was, let's say, 5 volts or maybe 0 volts and the amperes were 15 amperes, okay? Now we have to draw a graph between voltage and current depending upon or taking these values, okay? Now at 43 volts, so if this is 0, this is the graph for voltage, which is x-axis, and this is the y-axis for the current, okay? And assuming this is from 0 to 45, okay? And on the y-axis we have from 0 to 15 amperes, okay? Now if we draw a graph between voltage and current to show the relationship between them, okay, at 43, the step 1, 43 is approximately, could be here, and current is 5 amperes. So from the y-axis, probably this is 5 amperes, okay? So this means this will cross over here, approximately here, okay? So this is the step 1. Similarly, we will draw points for the other steps. So what will happen that the graph will look like this one, meaning that the relationship between the voltage and current is represented through this graph. In other words, if you want to know that if there is a voltage across the PV module and how much current shall be supplying, this can be found out from this graph. Suppose if the voltage across the PV module is 35, okay, then the current shall be 14 amperes. So this is how this shows that the relationship between the voltage and current of the PV modules. But now this graph has two parts, okay? That means the relationship between the voltage and current have two parts. The first part is this one and the second part is this one. What this means? This means that the relationship between voltage and current from this point up to this point, okay, is reverse, meaning if the voltage is decreasing or if the current is increasing, the voltage is decreasing. So the relationship between current and voltage is reversed. Okay, this equation means that if the current increases, the voltage decreases. Okay, and this is what we have measured, and this is how the relationship between the voltage and current of the PV module works. Okay, in other words, if the load increases or the current increases, the voltage across the terminals will decrease. Now this relationship between the voltage and current of a PV module is up to certain limit. The reason is that every PV module has certain limit of supplying maximum current or supplying power to the load. Assuming that at this point, okay, assume that the voltage here is, let's say, 40 volts, and the current is, let's say, is 14.5 ampere. Okay, now beyond this operating point, in other words, when the voltage is 40 volts and the current being supplied is 14.5 amperes, the remaining capacity left with the PV module to supply more current is minimum. In other words, if we increase the load or if we try to increase the current towards the load, the current will not increase. And this relationship is given by this graph, this portion of the graph. Meaning, suppose if we further try to increase the current beyond 14.5 ampere, the current will not much increase because the maximum capacity, let's assume, is 15 ampere. So it will increase from 14.5 to maximum by 15 ampere. However, we can see the voltage at the terminals of the PV module is reducing. Okay, so let's assume we are at this point. This point means the supplied current is close to the 15 ampere, but the voltage may be, let's say, 25 volts. And this is the characteristics of the PV module. So in this graph, the relationship between voltage and current can be divided into two portions. This portion, you can say, is more active portion, or okay, more dominant, while this portion, okay, is dormant portion, where the relationship between voltage and current is not reverse or direct relationship. If we try to increase the current, if we try to increase the load, however, the PV module is not supplying so much current, but the voltage at the terminals of the PV module is decreasing fast. So within just range of 14.5 to 15 ampere, we can see that the voltage has dropped from 14 to 0 volts. Okay, so that's how the PV module behaves in two different areas. Now the question is, at what point the PV module should be forced to operate so we can extract maximum power out of it. Okay, now if you remember, we made a table, okay, voltage, current, and there were steps. Okay, 1 2 3 4, and voltage was here, current. Now the standard formula of power is P is equal to VI. Okay, if we multiply voltage with the current, this will give us the power being supplied by the PV module. And if we multiply on the fourth column, we calculate P V into I, meaning multiply voltage with current, these two parameters, and write the answer here. This will give us the power being supplied by the PV module. Okay, so once the values are received for the power for each step, we can draw a graph. Okay, now this, if we draw the graph, let's suppose we have another axis here of the power, and let's say the values of the power ranges from 0 to 600 watts. Okay, and if we draw the graphs based on these values, the graph will appear similar to this one. Okay, so this graph which we have drawn just now will be based on these values we calculate, that is the power calculated from multiplying voltage with the current. Okay, now this is the power graph, or the power being supplied by the PV module. Okay, Now this graph shows that there is a maximum operating point with respect to voltage and current, meaning that there would be a operating point which is this one, which has got the maximum value out of these values calculated in this table, okay? And this is called maximum power point, meaning this is the point where when voltage multiplied with current will give the maximum value out of all or the complete range of the PV module. So this point, which is actually corresponds to this point, is basically called the maximum power point on the voltage and current graph, and for the power graph it is this point. Okay, now we summarize all this discussion we have just gone through. We can say that the characteristics of the PV module, or the characteristics of the combination or the relationship of the voltage and current of a PV module, is such that at only one point this gives the maximum power. Okay, this means that at this point, when the voltage is, assuming it is 35, and the current is, assuming is 14.5 ampere, this will be giving the maximum power. So we must try to operate the PV module at this operating point, and this point is called maximum power point. Okay, and nowadays the inverters manufactured are such that there is internal algorithm running within the inverter which forces the PV modules, or which operates the PV modules at this point, so that the maximum power is extracted from the PV module. Okay, that means the PV module is never operated over this point. This is a voltage, open circuit voltage, and obviously this is the point where the current is zero, and this point obviously the voltage is zero. So the PV module shall be operating over this point, which is MPP point, maximum power point, and the inverter which has these characteristics, or which has this feature to operate the PV module at this point, have a particular algorithm or equipment or devices inside it, okay, which is called MPPT, maximum power point tracking, meaning they are always running an algorithm inside the inverter to operate the PV module on this point to maximize the power supply. Now the relationship between the voltage and current we have just discussed might change in case the solar energy changes. Okay, the relationship we discussed between voltage and current, and the graph we have just seen, it was this one when the solar energy assumed was 1000 watt meter per square. Remember, we discussed previously this voltage and current, assuming, though we did not discuss or did not point out that the sun energy was 1000 watt meter per square. But remember that whenever we are doing discussions, it is under standard conditions. The standard condition is standard test conditions, and standard test condition is that the sun energy being received is 1000 watt per meter square. However, in reality, the sun energy, you know it, we have discussed that it may not be 1000 watt meter per square. It may be less than 1000 watt meter per square. So in that case, what shall happen to the characteristics of the voltage and current relationship? Okay, and we can see here that it has got different graph. Okay, now if the sun energy is 800 watt meter per square, in that case this graph shall be the relationship. This graph shall define the relationship between the voltage and current, meaning in the previous case we assumed this was 15 amperes, okay, and this voltage open circuit was 45 volts. Okay, now if the sun energy is 800 watt per meter square at particular time of the day, or the time of the year, in that case this graph is in relationship, meaning the maximum current at that time possible to be supplied by the PV module could be, let's assume this is 13 ampere. Okay, so this value is 13 ampere, so it can't go beyond that. So in this case the basic relationship is same. The only difference is that the maximum ampere being supplied by the PV module has reduced to 13 amperes. Similarly, for if the solar energy is 600 watt per meter square, we can see that the graph is shifting down. Or let's assume that this may be, for example, it may be 11 amperes or 9 amperes or 10 amperes. So the at 600 watt per meter square of sun energy, the maximum possible current to be supplied by the PV module could be 11 amperes or whatever the relationship is defined by the manufacturer. Now, if we look into the our maximum power points, okay, this point for all these graphs, meaning that when the sun energy is different, we can see that the maximum current possible to be supplied by the PV module is changing drastically. For example, this may be 14.5 or 14 amperes. This point could be 13 or 13.5 amperes. This could be like 11, 10 or 9 amperes, okay? But the change in voltage, okay, is not much. So from here we can conclude that when the sun energy changes or when it reduces, the voltage available at the terminals of the PV module doesn't change much. This is possible. Suppose that when the sun is 1000 watt per meter square, this operating point, the voltage is assuming it's 40 volts, okay? And when the sun energy is 400 watt per meter square, the voltage could be maybe 37 or 36, okay? So here we can conclude that the due to the change of the sun energy, the current capacity of the PV module changes, but the voltage at the terminals of the PV module doesn't change. And this can be related to the power also, V into I, okay? Once, because the voltage is not changing much, however, I is changing, so the power is changing. When I reduces, the power reduces. So this comes to the conclusion that the power being supplied by the PV module will reduce when the sun energy reduces. Now, before I conclude this presentation or session, one more thing I would like to add here is about the temperature coefficients of the PV module. Now, this data shown over here is taken from the same data sheet which we discussed moments ago in regard to while calculating power under different sun energy conditions. We took the rated power and dimensions. Similarly, these temperature coefficients are taken from the same data sheets of the Canadian Solar. Okay, now the temperature coefficients basically define the relationship between the given parameter and temperature. For example, this one, temperature coefficient P max, okay? Now this is minus 0.34% per degree centigrade. Now this parameter has minus sign. Minus sign means that the parameter shall decrease. Now how much? It is 0.34% against per degree centigrade, meaning that for each increase, okay, for each increase in degree centigrade or the temperature of the PV module, the rated power of the PV module shall decrease. This is minus, so we will say it shall decrease. How much? It shall decrease by 0.34%. Okay, so now let's assume the rated power is 640 watts, okay, in the data sheet, in the same data sheet we discussed. Now remember that always this data given in the data sheet is as per the STC condition, meaning that the rated power given by the manufacturer is only applicable if there is STC condition, or in other words, sun energy being received is 1000 watt per meter square and module temperature is 25 degrees centigrade. If any of these parameter changes, okay, the rated power will change. The PV module shall not supply power as given in the data sheet. Now for a moment assume that the sun energy remains constant 1000 watt per meter square, but the module temperature is increasing, okay? Assume that the module temperature increases to 45 degrees centigrade. So there is a change of 20 degrees centigrade, okay? Now the question is how much power shall be reducing? Okay, writing again here this parameter minus 0.34% per degree centigrade. Now minus is basically for just to indicate that this parameter or the power parameter shall decrease, okay? So we can remove this, okay? Now let's calculate how much in percentage the rated power shall decrease if the temperature of the PV module increases by 20 degrees centigrade. So we will simply multiply 0.34 by 20, and this comes out to be 6.8%. Okay, so the change in temperature of the PV module is 20 degrees centigrade, and as per this coefficient, we took 0.34% and multiplied it with 20. It comes out to be 68%, meaning that the rated power, okay, 640 watts will change by 6.8%. So if we multiply 640 with 6.8%, this is approximately 43 watts. Okay. In other words, if the temperature increases to 45 degrees centigrade, there is a change of 20 degrees centigrade in the temperature of the PV module. Okay, the rated power shall not remain 640 watts as specified by the manufacturer. The manufacturer is saying that use this temperature coefficient, this one, and find the rated power. So the rated power of the PV module has decreased by 43 watt. In other words, if we subtract 640 from 43, this is approximately 600 watts. So the change in 20 degrees centigrade has brought the rated power of the PV module to 600 watts. So in our calculations, we shall be using 600 watts, and that shall be very much fair value in our calculation to be used to, in case you want to conclude the rated power or some other thing. Okay, similarly, the temperature coefficient for the voltage open circuit is also given. This means it is also negative sign. Okay, this means that the voltage open circuit shall decrease by 0.26% for every increase in degree centigrade of temperature of the PV module. And this can also be found out in a similar fashion we have just done for the power. With this, we conclude this presentation or session, and we hope that you have learned few useful things. And if you are interested to know in-depth details and theory behind the solar PV systems and related technology, we have a number of short courses for you over a couple of websites. The details of these websites is given on this slide and is also available in the description over here. Registration at Electnology is free, and you can take up free and paid courses at your will.